Okay, welcome. This is a video I'm making for my students that are being quarantined or ones that are at home or independent study. The first thing, because you can pause this at any time, we're starting what we're called free body diagrams, or at least force diagrams. Technically, we're doing our force diagrams, if there are any engineers watching. But introduce you to some of the equations we're going to be doing. One of the biggest differences between forces and linear motion or projectile motion, things we've done before that, is that we always had equations where we just had to figure out the variables, and then we put them into well-defined, repeatable equations, like we did the fourth equation, second equation, strategy. What's different about this is we won't know what our equations are until we draw what are called these diagrams that show us the forces. The forces will allow us to plug into, I'll explain this in just a moment, a framework of how to figure out what our overall forces are, both in the x direction and the y direction. Also, the direction that those forces are, right, left, up, and down, will decide whether or not we are going to add them, right and up, or we're going to subtract them if they're going left or down. So the first thing is we analyze the situation, we look at the problem, we identify what forces are present, we draw them in the correct direction. For example, force of gravity is always going to be down, so that means in that case we would be subtracting that value or whatever that variable is. And then once we have the equation, then we just plug and chug. So we say that the most complicated step, I'm saying, well, eventually I don't want anybody to think it's complicated, to say, oh, I understand it. But the biggest jump is there's not just some equation where you can just pick out of that. You have to form your equation based on the diagrams that you are going to draw. So this is not just a universal. This is how I kind of express this. This means the sum. This is sigma, Greek letter sigma, and this means the sum of all the forces in the x direction. And when I say write your equation, this is really the part of the equation. This is just denoting that you are looking at all the forces in the x direction, the overall, also known as the net force of that in the x. So all the forces we have that are going to be moving to the right, we're going to add. All the forces that are going to the left are going to subtract. That net force, because Newton's second law says that F equals ma, force equals mass times acceleration, that the amount of force we have is going to decide how much acceleration we have, or how much acceleration we have will tell us how much force we need. So we're going to use the equation to figure out what our forces are, and that overall force will equal mass times acceleration in the x direction. We also have this in the y direction, where we say the sum of all the forces in the y direction. We're going to add all the forces up. We're going to subtract all the forces down, and then that net overall force is going to equal the mass of the object times its acceleration in the y direction. Now, a of y does not necessarily equal 9.81. It means, for example, a of y, acceleration in the y direction, would be something where, let's say you have an elevator, where the elevator is accelerating upwards at 3 meters per second squared. That means a of y would be that. If the elevator were moving at a constant velocity, or if it was also at rest, constant velocity, that means that would be 0. So we'll look at different examples. The other part here is understanding what we mean by balanced and unbalanced. If your forces are balanced, okay, that means the net force, that means overall all the forces are balanced, then that means there's no acceleration. Okay, if you have one arrow that is longer than another arrow, then they're going to be unbalanced, and that means that you're accelerating. Okay, so your acceleration is not 0. So if it ever says it's at a constant velocity, whether that means that it's at rest or it's already moving in a straight line with the same speed, that means the acceleration is 0. Okay, 0, 0. And if it is unbalanced, then it's a possibility that these are not 0. Okay, next thing we're moving on to is these are the forces we're going to be using in this class. And you're going to have to memorize how to write these and then really know what they are. So I put these key words off to the side. So we say, how do we know if we have these? It should be repeatable, where you're going to go through, do we have a gravity? Do we have a surface? Do we have a table? Do we have friction? Do we have, all these other things? So the first one is the force of gravity, F of g, that is also equal to your weight. The equation for the force of gravity is mg, and it makes sense that if force equals mass times acceleration, then the force due to gravity would equal mass times the acceleration of gravity, and we don't use a of g, we use g for that. But another big change is that G is positive 9.81, and this is counter to everything that we've been doing up until this point. So I want to make sure that I spend just a little bit of time explaining why in the world are we suddenly making gravity positive. And it's not necessarily we're saying making gravity positive, we're just saying that it's not going to have a direction. So let's take a little example here. So why we're not using negative. The reason why we use negative in linear motion is because we had to tell the equation that the object that was being pulled down by gravity. Let's say we have an example, just simple example here, where this object has the force of gravity downward. Okay? Don't mind the bell. F of G equals mg. It's down my prep period, so don't worry. And so if we were writing our equation, the sum of the forces in the y direction, there's no forces up, so I'm going to put a placeholder of 0, and I have minus the force of gravity. We're going to go ahead and ignore the MAY for right now. All we're concentrating on today is writing our force part of the equation, so this would technically equal m times a of y, but we're going to ignore that until a later date. Well, let's go forward and take this and say, what if we said, so let's just hypothetically say the mass is, mass is 2. We're just making that up, 2 kilograms. And let's see what it looks like if the acceleration is a negative 9.81 meters per second squared. 0 minus f of g is the same as 0 minus mg. And if I plug in 0 minus 2 times negative 9.81, we have to realize, what is this negative telling me? Has somebody said in 6th period that you're subtracting? Yes. But it's telling me that this force is going down. This is saying that we have nothing up and we have force of gravity going down. So remember, that's important. That negative tells me it's going down. Now, if we carry this through and we say if we use this, we get 0 minus 2 times negative 9.1. Those two cancel out, and we get a force of gravity that says 0 plus 19.62. That doesn't make any sense, because if I were looking at your work, or if you were looking at your work and you saw this positive here, that means that your force of gravity somehow is going up. So the reason that we're not using the negative here is because we are using the equation. Okay, the equation is telling us what the direction is going to be. It's based on the forces, and we drew this force going downwards, so we already know it's going downwards. That's why we subtracted it. If we're also going to say that gravity is downwards, those two negatives there in the math are going to cancel out, and you're going to incorrectly come up with the conclusion that the force of gravity is going up, and that is going to mess up all of your work. So it's not like we're saying, hey, gravity is now going up now. No, we're just saying acceleration of gravity is 9.81 meters per second squared, but we're not giving it a direction. So that's what I mean why that's positive. We're not telling it direction, because we're already doing it here. If we do it twice, it will undo what we're doing. Okay, so that's why that's positive. Let's go on to the next ones. Next one is called the normal force, and that doesn't mean opposite of unusual or odd. Normal in mathematics means perpendicular to a surface. And so when we think about this, look at some situations here. Normal, if I have a surface here that's flat and I have an object on top, the normal force is the force, so we would have force of gravity down, but the table or the surface has to actually be holding it up, so you're going to have a normal force that is up. Now, a common misconception is people say, oh, normal force, force of gravity, they're always opposite each other, that's why it's there. Well, let's look at a situation where we have it at an angle, okay? In this situation, the force of gravity would still be straight down, but we have to think the surface is trying to prevent it from going through there, so here is that, perpendicular to this is this way, so that would be the normal force that way, okay? Even we did an example, I showed a demo in class here. If this is a wall and I have a book, let's say that I'm, I'm going to have to draw a hand here. There we go. A hand is pushing it into the wall and keeping it up. Force of gravity would be straight down, and the wall or the surface would actually be pushing back at it. So that would be the normal force. So it's always perpendicular to whatever the surface we have. Okay, next one is tension force. So if we have a rope or cable, tension is always going to be going away from the object. If I had, for example, if you had a wagon that you were pulling with some type of a rope here, and here's the string. The only way to actually pull this and get tension in the rope here is if you were pulling away from the object. If you try to take this rope and you pushed it, you can't push a rope. If you try to push a rope, it's just going to go slack. So it always has to be going away out of the object, and that's what we mean by that. So if we have a rope or cable, that's the tension force. The next one is friction force. Friction we're going to go more into next week. There's two types of friction. There's static and there's kinetic. For this packet, we're just talking about kinetic, which once again we won't know what I mean until our next video here. So friction force, this is talking about moving. When we're moving, that's kinetic, and it always opposes the direction of travel. Friction will try to remove the energy out of some object by slowing it down, or I guess resisting the motion. Okay, so if the object is moving, if it's something is sliding, if we had, for example, if this box here was being maybe pushed to the right, that means that if it's moving that way, that the friction force would be back to the left. Okay, it always opposes direction of travel. Even in the case of this one, let's say this block was sliding down here, and if there was friction, that means friction would be in the opposite direction of travel. Okay. And then generic force, F sub A is the applied force. That's just if you say there's just a generic push, and it's not one of these specific. We also have air resistance, and really outside of this packet, we never deal with air resistance, so I'm just going to kind of gloss over that. Air resistance is very similar to friction force. Air resistance is something that you would study if you took AP Physics, so you can use that time. There are directions here that we're using to solve for our free body diagrams, and they're going to be to draw the free body diagram. Now, if there are people watching this and saying, "Wait a second, here's a free body diagram I drew here. This is technically not a free body diagram. Yes, do I have the forces? Am I labeling them? Are they correct? Yes, but if you wanted to be technical, engineering-wise, this would be the free body diagram." You're saying, "Well, what's the difference?" Well, this is a picture, and this is just some box representing the object. I'm totally fine with you drawing the forces on there. I think it helps, especially in the beginning, if you actually, instead of drawing something like this, you can actually understand what is the scenario is going on there. Okay, that we have two cables going up and the girl's being pulled down. That, yes, gives you a better idea, but the picture makes it a little bit more obvious. You're also going to correctly label the forces. You're going to draw the arrows the appropriate length. I'll talk about that in a second here. You're going to indicate whether the object is CV or CA, so whether it's balanced CV or unbalanced CA for each direction, X and Y, and then you're going to write the equation. When I say write the equation, we're just writing the force equations, which means we're not yet writing MAX, MAY. We're just figuring out what is right, what is left, what is up, what is down, and then writing those equations. I'll show you an example real quick with this first one that I've already done in a previous class. But here, if we're saying we have a book, it's at rest on a tabletop. We have the force of gravity down. This is going to be balanced. Notice that it's not accelerating right or left. It's not accelerating up or down. So if it's not accelerating, if acceleration is 0, these forces need to be balanced, which is why this force has the same length of arrow this way. Mathematically, it doesn't really matter how long you draw those, but conceptually it does. If I wanted to show something was falling, let's look instead at, well, hold on here. If I wanted to show some object was, let's say it's falling, okay, force of gravity, and it had some air resistance here and there. This would mean these are unbalanced, and whatever arrow side is bigger, down in this case, means that is the way that it is accelerating here. Okay. If the forces are balanced, it's not accelerating. If the top arrow would be bigger, that means it would be accelerating up, and so on and so forth. So what we'd be doing in this practice, it was saying in the x direction it is CV, constant velocity, it's not accelerating. Some of the forces are 0 minus 0, or you can just say that the sum of forces in the x direction are 0. In the y direction, up and down, it is also CV. Okay, it's not accelerating up or accelerating down off the table. So the sum of the forces, or all the forces up, are added, F of n. Subtract all the forces down, F of g. So that would be my equation. That's where we're trying. We're trying to link picture, forces, equation. Picture, forces, equation. Picture, forces, equation. If you can create this equation, everybody's shown to me clearly that you can do the math. We'll look at one other one here before we look into the next page. I don't want this video to be too long. Try to keep it under maybe 20 minutes or something. Here we have a girl suspended motionless from a massless bar which hangs from the ceiling by 2 ropes. I'll cover this part because I don't want to see that. Hey, we have 2 cables. It says ignore the mass of the bar. I guess another way of looking at this is that this is the girl. She has her force of gravity. She has her weight pulling down, and there's 2 cables. Now, a question that I asked in class is, I asked them, why do you think I'm drawing conceptually, why am I drawing these 2 forces? This arrow is clearly shorter than this one. Well, the reason is, if this is really going to be motionless and these forces are balanced, then that means that the length of these 2 have to equal this. Or mathematically, if this is, say, 100 newtons, both of these would have to be 50, and they would have to add up. Or even if the tensions aren't the same, the combination of this force plus this force has to equal this force down here. So even if we're not assuming that they are the same, that's what's happening. Okay, in the x direction, this also one doesn't have an acceleration in the x direction, so it's some of the forces are 0 in the x direction. But in the y direction, we also have constant velocity. So I would have tension up plus tension up minus force of gravity. Okay, so I'm going to cover the other part here. There was something we discussed in class. Let's move on to 2 other ones. I've loaded this paper up already. I believe I loaded on one of the pages on this folder in Schoology. So don't mind the flying squirrel. Flying squirrel is it's a joke we have. It gets steadily and steadily worse. So this is the flying squirrel picture I had in first period. Then I had to up my game. This is the one I had in 4th period. And then eventually I got to find the one I had from 5th period. Right. 5th period, we decided to add some ammunition to the flying squirrel and some bombs and some seats and all that. And then 6th period, we had some lasers, and then this was now a bomb compartment. So yeah, there we go. Got to have some fun sometimes. But we'll look. We're going to look at number 5 and number 6 here. Okay, so number 5 and number 6 are very similar to each other, and I already have everything written. Okay. We're just going to kind of look through this. It says, a rightward force is applied to a book in order to move it across a desk. Both of those say that exact same thing. This is basically the same from there to there. However, number 5 says it is with a rightward acceleration, basically saying that our a of x is going to be a positive number. Okay, we're still only concentrating on this part of the forces. I'll discuss the parts that are in blue here a little bit later. Okay, so we do have an applied force. It's rightward acceleration. It says consider friction, so we'll have friction and we'll neglect air resistance. So if I was going through my checklist saying, do we have gravity? Yes, it's downward. Do we have a surface? Yes, perpendicular is upward. Even though it's accelerating, it's only accelerating to the right, which is why these 2 arrows are the same length. Okay? There is an applied force, so I drew my applied force over to this side. But it said it was accelerating. That's what I was talking about. If it's accelerating to the right, that means that the arrows to the right have to be greater than all the arrows to the left. So in this case, we have an arrow to the right, the applied force. The friction force has to be smaller than that. There's one side that's bigger than the other, and that's going to cause the book to accelerate in that direction. So before we write the equation, now let's look at number 6. Number 6 is almost completely identical. The only thing is that it doesn't have an acceleration now. It's not a constant velocity, which means that these have to be balanced. Unbalanced, you're accelerating. Okay, they're unbalanced. Balanced, you're either at rest or you're moving with a constant velocity. So my applied force, notice I drew it the same amount here, but now the friction force is the same as the applied force. It doesn't mean that it's not moving. It could have already been moving. It just says it's not going to speed up, it's not going to slow down, it's not going to change direction. We actually look at the equations here. It's pretty interesting that although one's accelerating and one's not, the force equations, the forces that are on them are acting in the same direction, and so the equations of the forces are actually like the same. In the x direction, it is CA, so we have it's always right minus left. FA minus FF, okay? But notice we also have it here, FA minus FF. Now you may be saying, that's kind of useless. We know these are two problems that are obviously not the same. Why do they have the same force equation? Well, once again, we're not writing the whole equation quite yet. We'll start that next week. This is the whole equation if we include the mass and acceleration. So this would be the whole equation. And if we look, how are these different? Well, in this case, if it's at a constant velocity, that means that the acceleration here is 0. And so you would have FA minus FF equals 0. And here we have FA minus FF equals mass times some number. Okay, some number that's not 0, which shows that this whole entire equation is different than here. Okay, so there's the force part of it, and then there's the mass and acceleration. So we're just concentrating on this, but I'm kind of showing you more of the info of why they're not the exact same equation, even though the forces are going in the same direction. Okay, because notice that this equation doesn't actually show how big FA is compared to FF. It just says that one is going to the right and one is going to the left. So you can't necessarily look at this and say, oh, clearly you drew that bigger than that, so that's why it's different size. That's not it. In the y direction, it's not accelerating for neither of them, so it's constant velocity. We have Fn minus Fg, Fn minus Fg. And in this scenario, in the y direction, these are the same exact equations because it's not accelerating up or down here, and it's also not accelerating here. Notice that all the ones where it is a constant velocity, your mass times acceleration cancels out because your acceleration is 0, it's 0, it's 0. And so when we have the acceleration, we have this, but if its acceleration is 0, we cancel that part out. Okay, so we're going to go over more of that next week. Monday or Tuesday, I plan, so Monday, Tuesday, next week, I plan on going and talking about friction. And so we'll talk about what makes up friction. We'll continue, this packet continues on here. We'll even stretch it possibly a little bit further to even introducing what it looks like when it's on an inclined plane. But we'll probably hold that off. So I'm going to go ahead and stop the video here. You can pause it, you can do that, but you are going to want to fill this out. This is a packet here, so if you have to pause the video and just write what I have, you can clearly go along if you want to as well, but we're going to go ahead and pause the video. So I appreciate it. Check out, this will be posted on Schoology, but the link will be to YouTube, so keep checking back on YouTube or subscribe or whatever so you can know when those come out. Appreciate it. Have a good weekend. If you're doing trick-or-treating things, make sure you're safe. So appreciate it.